So last time I kind of lied to you a little bit. I wrote an expression wrong.
We're used to it.
Used to, ouch.
Just used to being lied to. It's fine.
So it has to deal with where we were talking about the Schrodinger equation. We were trying to separate things. Where we had negative h bar squared 2 mu r over r er r squared plus 2r over big R er d little r plus, I think I had v plus h bar squared l plus 1 divided by 2 mu.
Isn't that VR?
You have
Shouldn't
VR
there be
squared.
R's?
The second term?
VR squared. Okay. And was it like this?
Equals to ER squared.
I'm sorry, can you say that one more time, Maddie?
Yeah, you just had it, yeah.
Okay. So something I messed up is there actually should be an R squared down here. And at one point I wrote out this V effective thing. And I said negative z e squared 4 pi epsilon over r plus L times, h bar squared times L plus 1 divided by 2 mu r squared. And I said this was just defined through the math. This r squared up here actually should have been down here. That's why these are equivalent to one another. We just conglomerate everything into one v effective. Because if we look, this expression depends on r and the value of L. Okay? Does that make sense? I just wanted to clear that up. It doesn't really matter in the bigger picture of things, but in terms of mathematical sense, I wanted to make that very clear. Okay, what else did we talk about last time?
That was a while ago.
Yeah, I know, it feels forever ago.
The known solution.
Yep, so we have a known solution, and it was those Langmuir polynomials.
Are those like Lagrangian the same thing, or is these different?
It's different.
Okay.
So Lagrangians are something else.
Okay.
And we said these polynomials, what do they depend on?
Oh, they're dependent on n and l.
Yep. Okay. And the
N
other,
has to be bigger.
yep. N has to be bigger than L. Those were the only rules that are mathematically set up. And then we said that we can look at the wave function, and the wave function has 2 parts. And what were those 2 parts again?
Angular and radial.
Yep, so there's an angular part and a radial part. And the radial part, that's where N and L matter. The angular part, what quantum numbers matter for the angular part?
L and ML.
ML.
Yep.
Absolute value.
And it had to be less than or equal to L, right? Okay. Did I send you guys a picture or anything of those wave functions? Yeah.
No.
No? Okay. So we'll talk about these in a little bit, and we'll use them in a little while. But again, we have to keep track of N and L, and then the corresponding radial part changes. What is this E up here? The E is defined as 2 times the the atomic charge times the radius divided by n times a. And what a is this expression here. So it's a bunch of complicated nested constants in one another. For your guys' Quizlets, these will be given to you. All this information will be given to you, okay? What's important is to know that you have to look up these values. All right? Okay, so I'll send you guys a sheet that has those in it a bit later. Okay, so we're going to talk about the energy expression for a hydrogen atom and how it connected to the Bohr model of the atom. Can someone tell me a little bit about the Bohr model of the atom? Like, what do you remember about it?
It was actually decent. Had the nucleus at the center, positively charged and small, with some sort of positive charge going around it.
Yep, and then
or negative charge.
Yeah, and then the electrons were out here, right? And they followed these discrete quantized orbits. N is equal to 1, and they could have excited states if it was a hydrogen atom. N is equal to 2, and so on. And you could calculate, and we actually did calculate this radius that was along here. And we called that A sub O, and A sub O was known as the Bohr radius. And so this is assuming this is the distance the electron is away from the nucleus, assuming they follow these discrete quantized orbits. But what's the problem with the Bohr atom?
It assumes that the electron follows a constant radius.
Right, and why can't that be true?
The Heisenberg uncertainty principle.
Yep. So because of the Heisenberg uncertainty principle, that can't be true. But we're going to find something interesting out today as we look at the energy expression and we look at the most probabilistic spots that an electron can be found for a hydrogen atom. Okay, so it can be shown that the energy expression that you guys used, E sub n, is equal to negative mu e to the 4th divided by 32 pi squared E naught squared h bar squared times z squared over n squared. So this is an expression, we can show that this is true, where, what was mu again?
The mass.
I'm sorry, I couldn't hear you.
Is it the mass?
Yep, specifically what type of mass? Starts with an
Rest
R.
mass. Rest mass.
Not rest mass. Other one.
Reduced mass.
Yeah,
Oh,
reduced mass. Yep, it's a reduced mass of hydrogen. So that's equal to 9.104 times 10 to the minus 31 kilograms. Okay, so we're going to ask a question. Can we simplify any of these constants? And we're talking about a hydrogen atom. So, oops. What can we do? So if discussing each atom, we can conglomerate all of this stuff. So this whole front expression here, whoops, what do we notice about it?
All constants.
They're all
Yeah.
constant.
Yeah, they're all constants. So e to the fourth mu 32 pi squared epsilon naught h bar squared. If we look at these values, we have 1.602 times 10 to the minus 19 coulombs to the fourth, 9.104 times 10 to the minus 31 kilograms, all divided by 32 pi squared, 8.854 times 10 to the minus 12. Does anyone know the units of the permittivity of free space?
Probably did at some point.
Yeah,
Probably over coulombs, kilograms.
close. Coulombs are actually up top. Joules times meters on the bottom. And then you guys know H bar. What's H bar's units?
H bar is joules times seconds. Is that right?
Yep. Okay.
Where did you get the coulombs for E? Up top.
For E, if you look
Yeah,
at
like what-
one, this comes from Faraday's constant. So if you look at 1 mole of electrons and then you whittle it down to a single electron, you can get to that value.
Okay.
Where did the negative go?
We're leaving it off for now.
Okay.
Okay, so if we combine all of these numbers, the value that you get is 2.178 times 10 to the minus 18. And can you guess what the unit is going to be? Thinking back to
Newton.
this expression.
Joules or coulombs?
Yep, it's joules. Have you guys ever seen this number before? Way back at the beginning of the semester. I know a lot's happened since then.
Thanks, my friend.
Ringing any bells for anybody?
Probably once you write something down, I'll recognize it.
Oh, yeah.
Yeah, exactly. This is actually the Rydberg constant.
Oh, of course.
I recognize that word.
R sub H. So remember, when Bohr was considering the model of the atom, he was looking at delta E is equal to R sub H, 1 over Ni squared minus 1 over Nf squared. You remember that expression?
Yeah.
Yeah. So what's crazy is they had to determine this empirically. But what we have done is we've determined it theoretically. So we arrived at an empirical constant. So something that had to be measured through experiment. We've gone through a process where it's all been completely theoretical or from first principles, also called ab initio. And we have arrived at something that we can experimentally measure, which is pretty cool. Okay. So now the other constants. Are based off of, we're going to make the symbol E or rho, which is dimensionless. And the way that we're going to define rho is 2zr over n a, where n is that quantum number, and a is another constant. A is equal to mass of electron divided by the reduced mass times A naught. And what A naught is, that's the Bohr radius. And it also is another set of constants. H bar squared, mass of electron squared, and it ends up working out to be 0.529 angstroms.
Is that E or L? I'm sorry.
That is E.
The dimensionless one.
Oh, this thing?
Yeah.
That is a rho symbol.
Oh, okay.
So Greek letter.
For A, is that equivalent to ME over mu?
Yes.
Okay.
E. There we go. We'll try a bit better. There we go.
And then on the bottom of that, is that E squared or is that the
Yep, that's
rho?
E squared. That one's
Okay.
E squared.
I was about to say.
We'll write rho
Like
in a different color from now on. I'll
okay.
highlight it. We'll put it in green. There we go.
It's like Christmas.
Yeah, I feel Christmassy. I was wishing it was Christmas the other day. I don't know why.
A quarantined Christmas would be awesome. Wow.
Christmas is awesome. Okay, so we can simplify this expression a little bit. Let's look at it a little more closely. So if we have 1 over mu, that is actually equal to 1 over the mass of the electron plus 1 over, what's the other mass we have in this system?
Mass of the
Reduced
nucleus.
Yeah, nucleus. We're going to put that with a capital N. So now if we manipulate this around, let's say we want to look at this expression here. Mass times E divided by mu. So mass of E divided by mu, we're going to get mass of E plus 1, mass of E, mass of N. Okay, what do we know about this first part?
0 or 1.
Yep, comes 1. Now, what about this part? We could plug in numbers and we could check this, but what do we know about the mass of the electron compared to the mass of the nucleus?
It's equal.
Not equal, that's
Mass of
charged.
the nucleus is like much larger than the mass of an electron.
Right, so mass of nucleus is way larger than mass of the electron. So what could we say about the magnitude of this term?
0.
Yeah. You can approximate it to be a 0. It's very small. So if we were approximating this expression, we could say, what's this portion equal to?
1.
Yeah, we could say it's equal to 1. So what do we know about A and A naught?
They're about the same.
Yeah, so therefore, we can assume in most cases that these two are approximately equivalent to one another. So that's going to make our life a little bit easier.
How do you get 1 if you're dividing by 0? Wouldn't it be undefined?
Oh, this whole expression is approximately equal to 0. Does that make sense? Not that, I'm sorry, the way I drew it, you're right. It looks like it implies mass of nucleus is equal to 0, but it's not. It's this whole term that is. Okay, so we're going to use that in a minute to come up with an expression. Okay. So before we go any further, what we're going to do is we're going to ask some questions about what does the wave function look like for a hydrogen atom. And we have to specify different orbitals and so on. Okay? All right, so first question. What does the wave function of a 1s orbital or an H atom look like? So first, let's determine what things, so we're talking about an H atom, right? So we got that nucleus, we got some electron, it's out at some space. We have a distance that nucleus is, an r, or excuse me, a distance between the nucleus and the electron. Then we have the angle at which that electron is in this direction and then in this direction. So I think we called this one, what do we call this one? I think we called it theta. And this one, phi, right?
Sure.
Okay, so now we have to determine what this wave function is going to look like. What does the wave function depend on?
The
We got phi,
movement of the electron.
R.
r, yep, and what else?
Theta.
Yep. Okay. Now, we said we can break this up into two portions. What are those two portions again?
The
Angular.
and
Yep.
radius.
And do you remember what symbol we gave the angular or what symbol we gave the radial part of the function?
Radial is phi, angular is phi.
Nope. Angular depends on all the angular parts. So that was given the symbol y.
I was right anyway.
Isn't it like Y, L, ML?
Mhm. Yep, L and ML. What about for the radial part?
Isn't that just a big R?
Yep, big R. That depends on little r. And what else do we need there?
Maybe N?
N and what else? Yep. Okay. So now we're talking about psi of a 1s. So R, what are we going to have for N value?
One,
Yep. L value?
0,
Yep. And then we have the angular part. What's our L value again?
0,
M sub L value?
0.
Yep. Okay, so we have to look these things up in our table. So let's look up the radial part first. Okay, so that's where we would have to go to a table. Luckily, I have one right here. So we need this expression. So we get 2ZA 3 e to the negative rho divided by 2. And rho is defined as 2ZR over NA, and A is defined as 4 pi epsilon naught h bar squared u e squared.
That's e to the negative p over 2.
Yep, negative p over 2 or rho over 2.
Rho over 2? Okay.
Okay, so we got to plug in, we got to solve for these things, right? Okay, so we got this expression. Let's sub these two parts into one another. So we got rho. We have 2ZR N, and then we have A. So we have 4 pi epsilon h bar squared all over mu e squared. Can you simplify that expression for me? Or tell me what's going to go up top, what's going to go on the bottom.
Mu and e squared go up top.
And the N, right?
We could do that. Any other tricks that you would suggest? What do we know about A? Or what did we show previously?
We showed that it's equal to a naught.
Yeah, we could approximate it to be A naught. So instead of solving for all this crap here, let's just say that that's true. Okay, so that's our expression for rho. So let's go back to the radial expression. 2ZA. How's this going to change? We're approximating A is equal to A naught. So what has to happen to this first term here? Or what I have written, is it correct?
So it'd be 2z over a naught.
Yep, it should be A naught in that case. Then we get e to the negative. What's going to follow in place here?
2ZR over NA.
Yep, A naught. Okay, we can simplify this a bit further. What else could we do to make this portion more simple?
Should the 2 be gone because it's negative p over 2?
Oh yeah, there is a 2 down here. Yep.
So the 2's cancel out.
Yep, 2's cancel out. Forgot a 2. What else? So let's look at these things. What's Z again?
The effect, what's the effective charge? So like
Well, it's nuclear charge in this
nuclear
case.
charge, yeah.
Yep, so what's Z equal to?
1.
Yep, because we're talking about a hydrogen atom. What's R again?
The radius.
0.529 angstroms.
Well, that's the radius. Remember, it's fuzzy in this system. So it's
Okay,
just,
so we're not having it. Okay.
yep. N, what's N in this case?
1,
Why 1?
because it's a 1s.
Nice.
Yep. We're talking about a 1s orbital. We've also specified it here. And A naught is just some constant, right? So what are we left over with then?
Just r over a naught, negative r over.
Yep. Negative R over A naught. Cool. So we've taken this extremely complex expression and we've distilled it down to this. Okay, so that's the radial part, right? And now we have to deal with the angular part. 0, 0, theta, b. And I think you guys can look that up. Does anybody have that table near them or open right now? If not, I can pull it up here. So this is keeping track of our L and our ML values. What is our L and what's our ML value?
0, 0.
0, 0. So what's the radial part? Or excuse me, what's the angular part?
1/4 pi to the 1/2.
Yep. So this is 1/4 pi to the 1/2. So now what does our total expression look like then?
Just those two expressions multiplied together.
Yeah. Bohr wave function for 1s of a hydrogen atom should be equal to 1/4 pi times z over A naught 3/2 times e to the negative r A naught.
Times
We've got one thing in here though. What did we forget?
Times 2.
Times 2. Yep. So let's simplify that then. What's this going to become?
That'll become 1/2. So come out. So it'll be radical 1/pi times z over a sub 0 3/2 times e to the negative r over a sub 0.
Yep, exactly. Now this expression doesn't look too difficult to deal with. All it depends on is that R value. There's no theta or theta showing up, so life is going to be a bit easier for us. Okay, so let's utilize this in practice. Everybody feel like they get an idea of how to do that? Like if I were to give you, I don't know, a 2px, you feel like you could do that?
I've not. Well, you just gave us like the most simple system. I'm pretty sure because it's hydrogen at 1s. So like I don't know. I guess I would have to see.
Okay, so like let's say we were looking at, I don't know, a 2px.
And this is for hydrogen? Or...
Yep.
Okay.
Yep, for hydrogen.
Because
you can have those excited
I like that
states.
idea.
Yeah. So you would have to look up the angular part, but what about what would the radial part be?
It would be 1, or it would be 2, and then
Yep. 2. What's our value of L?
1.
Yep. And then we have the angular part. And the angular part you can look up. What is our L value
1 and
for
1.
a 2px?
1 or 0?
If it's 1, and then our m sub L, that's where it's going to depend on your coordinate system. I think in our case, the way that it's been defined, I think that's 0. Your book states it explicitly, but for the most part, I would just ask for that R portion, and I would most likely tell you the L, or M sub L. But then what you'd have to do is look these things up. So the angular momentum portion, you use this table. We would go with that guy. And then for the R portion, which one of these expressions would we use?
The third one.
Yeah.
Third. So why do we know it's 2 than
Oh,
1?
not the third one.
First one.
Nope, not the first one.
Or didn't we say
Isn't
it was
it 2, 1?
Oh, it is the third one. Yeah, you're right. Sorry, I can't count.
So why is it the third one and not the second one? I guess.
Because the
How do
second
we
one, what's our
differentiate
value of L?
0. Well, how do
0.
we know that our value of L is 0 or 1, not 0?
So, oops. We specified a 2px, right?
Yeah.
We're saying a p orbital. What's the value of L for a p orbital?
Oh, p orbital is okay. Yeah.
Yep, what is it?
It's 1.
Yeah. So that's a p orbital. And what about if L is equal to 0?
That would be a s orbital, so that
Yep.
would be 0. Yeah.
What about L is equal to 2?
It's a d orbital.
Yep.
Okay. I forgot about that. We're good.
Okay, so everyone feel like they could construct, whoa, didn't mean to pull that away. Everyone feel like they could construct at least this portion and then start conglomerating stuff.
Yeah.
Okay. All right, so now let's use that expression that we just found and some of the other ideas that we've had in the past. How much time do we got?
3 minutes.
5 minutes.
Got 5 minutes? Okay, we're gonna try to go through this quick. Our example, we're gonna say, what is the probability that an electron in the 1s orbital of a hydrogen atom will be within a radius of 2.00 angstroms from the nucleus?
Can't find a good place for my little pictures of you guys.
I know, I hate that too. I keep covering stuff up. I put it on my other screen, but then I'm like looking over here at you guys.
It's always like in the way.
Okay,
I'll move it over.
minimize it. Awesome.
Okay, so what are we looking for in this problem?
Probability.
Yeah, we're looking for probability. Okay, how do we find probability?
Probability
Phi star times phi.
integral from a to b
Yep.
of psi star psi tau.
Okay. So we have to know our function, which we do know. D tau, what are we going to integrate across? Or how many
All three.
integrals? How many integrals will we need?
Will it be a
Guessing.
triple integral again?
I'm sorry, what was that, Josh?
Will this be a triple integral again?
Yep.
Like,
So-
what is it, like 0 to pi and then 0 to
Yep.
pi?
Yep, so we got theta, which is 0 to pi. We got phi, which is 0 to 2 pi. And we also have, what's our last
0
variable?
to 2, because it says it's a radius of 2.
0 to 2. Okay, then we have our expression, 1 over pi z a naught 3 halves e to the minus r a naught, right? Is this the complex conjugate, or does the complex conjugate matter?
No.
Nope, there's no I, so it doesn't matter. Z a naught 3 over 2 e to the negative r a naught. Okay,
And
we
then
need our, I didn't have enough room. What else do we need down here?
sine.
Yep, we need sine theta, d theta. What else do we need?
d phi dr.
Yep, and there's one thing that we forgot with our dr. What else do we need with our dr?
Was it just an r, a little r?
We need
Is it
an
a
r
squared?
squared, actually. Okay. So now, what we're going to do is we will go. Actually, we'll stop here and we'll go through this expression next time. The overall answer is 0.981, or if we wanted that in a percentage, what's that going to be equal to?
98%.
Yeah, 98.1%. So next time we're going to go through the mathematics of this and show how you integrate this guy. Okay, if you want, try it on your own. That'll give you an example to work with, but we will cover it next time. Okay?
What will our daily problem be then?
I don't know. Let me.
No daily problem.
Write how you
Let's
feel
see.
about the class thus far. Write one diamond.
Oh, in this one, it's determined the mean radius of a 1s orbital for a hydrogen atom.
Oh, okay.
Okay.
I mean, you could give us a word search one of these days.
Yeah, so we just have to solve for 0.5 then.
No. There's something else that you'll need.
Oh boy.
Okay. So there are examples in your book that you can check out to solve that problem. Are there any other questions?